Okay, good morning, welcome back. I hope we enjoyed the long weekend. So we start on page 48 today, if you could open there. And then I have a ton of announcements, but we're just going to wait a few minutes on the announcements. We'll dive into the material, and then we'll do the announcements once everybody has trickled in today. So let's go ahead and just jump in here on page 48. And we'll go here to number 1. And Sam, can you read number 1? Okay, thank you. So we're going to jump in on number 2. If you have your textbook with you, this would be a good time to take it out. Is there any table where there isn't a textbook at the table at all? Here, here, and here, okay. Any place where there is more than one textbook? Yes? All right, 2 of you guys, can you come up here for today? Ernie and Steve, you can just come up here. And Ashley, you can join Dave. Okay, do you have your textbook on you today? No, that's okay. We'll find somebody that does. All right, so you guys can just join up here. Okay, so let's just take a quick look at this table. So I've made a scan of it. Oops, that's there. There, okay. They don't have one, thank you. Okay. All right, so here's the table. So the top formulas are differentiation formulas. We're not looking at those right now. The first basic group of integrals are the basic functions. There are 7 of them. They're the same basic ones that we've been doing for many, many months. Then the next category is products of e to the x, cosine of x, and sine of x. Now, I don't want to get lost in the details of the formulas, but as you're trying to decide where your formula is located, your best bet is to first look at the bold, the categories. So looking inside of this list of categories, we see that we've got something here, e times sine, e times cosine, sine times sine, cosine times cosine, just to give you a sense of what those things look like. So if you are multiplying e's and sines or cosines, this is the category you look in. Okay, as we keep looking around on this sheet, the next category is products of polynomials with ln, e, cosine, or sine. So same idea as up above, but we're looking for now polynomials times everything. So in the first one, I've got any power of x times ln of x. That's a polynomial times ln. Then I've got any polynomial, that's what p of x stands for, times e to a power. And then if we go over to the other side of this page, up at the top it should continue, polynomials times e's or ln's or sines or cosines. So looking up at the top, we see a polynomial times sine. We see a polynomial times cosine, okay? So just, again, trying to get a sense of the basic locations of these different formulas, looking at the form that they have before we get lost in the nitty-gritty of the actual formulas. Okay, the next category, integer powers of sine and cosine. So that's going to be sines and cosines raised to powers. So sine to any power, there's the formula. Cosine to any power. Sine to a power, but in the denominator. A single sign in the denominator. How come that one's not covered in the previous formula? Isn't 20 just duplicating a special case of 19? What power of m is the power that will give us 19 turning into 20? Is m equals 1, so isn't it just duplicated? So if you look at 19 and you read all the way to the end, past the crazy formula, what does it say? It says m is not equal to 1. So apparently we need a different formula. It just doesn't work when m is equal to 1, okay? And then the same business down here in 21 and 22 for cosines in the bottom, and then finally sine to any power times cosine to any power. right? So multiplying sines and cosines together we'll find here. Okay, and then is there one more category here? Number 5, quadratics in the denominator. So here we're looking for two more categories. So here, number 5, quadratics in the denominator. You can see x squared plus a squared in the bottom with a linear thing up on top and x on the top. There's the same x squared plus a squared, but now it's just a 1 up on the top. Now we've got factored things in the bottom and either a 1 or a linear thing. So if there's a quadratic thing in the bottom, we look here. And then finally, integrands involving square roots of stuff that looks exactly like that. X squared plus a squared, x squared minus a squared minus x squared, and then crazy formulas that should look intimidating, quite frankly, at this point. But the first basic idea is to just get a general handle on the different kinds of categories that exist, okay? So let's see if we can do some integrals here with part A. X to the 5th times ln of x. So before you look for the specific formula on that page, think about what this is. This is a polynomial times ln of x, yes? There's a whole category of polynomials times, and I think one of the things was ln of x. So find that category. Everybody find it? Polynomials with ln of x. So what formula is x to the 5th times ln of x? What number? Number 13. Does everybody see? The integral that we're looking at looks exactly like number 13. You guys don't have a third book at that table, do you? No, okay. Let's see if we can get you guys one. Somebody comes in maybe. Okay, how much is n in number 13 for our example? N is 5. So we just have to copy this formula with n equal to 5. So go ahead and do it. You've got the blank space there. Just write everything in that formula where n is equal to 5. It was number 13, yeah. N is equal to 5. All right, so hopefully we've got something like 1 over how much? 1 over 6, x to the 6th ln of x minus 1 over 36, x to the 6th plus c. There's your answer. Now that formula right there, actually you don't need to use it. We integrated stuff with ln of x in it last class. What technique did we use? Integration by parts. I feel like you could prove formula 13 if you just very carefully do integration by parts exactly once. But we've got it. No need to reinvent the wheel every time. So we've got our answer for that one. Let's take a look at the next one. Part B, 1 over cosine cubed. We have seen cosines in the bottom. We just have to find that category. So find the category with the powers on sine and cosine. It was on the right-hand page, wasn't it? All right, so I've heard one vote for 21. Agree? Okay, so we'll take a look at 21. 1 over cosine to a power. How much is m in our case? It's 3. Now the bad news about this formula, before we get into the details, is what appears in the right-hand side. Another integral. So all you're doing is trading an integral for hopefully an easier integral. So let's just take a look at that easier integral, or that integral, and see if it's easier. We said that in our case, we're using 21 here. So we said m was 3. So then what power do we end up with on the cosine? It just becomes 1 over cosine to the 1, right? M is 3. So apparently using this formula drops the power on the cosine by 2. How do we integrate 1 over cosine? That still seems hard. It's number 22. So use number 21. It will give you a new integral. Then use number 22. See if you guys can work with your neighbors on that one. So again, we're using number 21, where m is equal to 3. So what does the first part become? 1 over 2 sine of x over cosine to the second, plus, and then what's this fraction? Is 1/2. Yes, m is 3. And then we got the integral, and we've already talked about how that integral is 1 over cosine of x. And then 1 over cosine of x, brand new formula down here in number 22. It is just that whole thing, 1/2 ln of that stuff. So just stick that together. What did we say this fraction was? Was it also a half? Yeah, so then a quarter in front of that ln. How do you mean? Oh, absolutely. Yeah, you can decide that you've already got an integral and you'll do that first. Sure. Any questions on using the one formula followed by the other? Okay, let's go back to the packet. And in fact, actually, this is a good time to do all our announcements. So we'll come back to C momentarily. But before we do that, let's just take our look at the calendar. So calendar is here. Today we're talking about tables of integrals. Next class, a couple of things are happening. Number one, the project is due. Project 3 is due next class. This is the one with 4 different area calculations. I encourage you to check your answers with other people in this class and the other section. Also, next class is due the take-home quiz. That was the formulas of all the derivatives and integrals that I want you to memorize. So anybody finish it already? Okay. All right, so just a couple of people, and if you haven't done it yet, just do it between now and Friday. To be honest, I'll take it on Monday without any penalty. The goal is to have it before the test. So I thought I'd pick Friday to try to get folks to act on it a little bit before so that you're not worrying about that at the same time as over the weekend studying for the test. But I'll take it Friday or Monday. Either way is okay. If you need extra copies, let me know. I want everybody to get 100 on that. Okay, and then also next class is our review for test number 1, and test number 1 is happening on Monday. Any questions on, yeah, Dave? Good question. So on the test, you actually get to use a full piece of paper, 8.5 by 11, both sides. Good. And page 1 of the packet. Other questions? Okay, next thing to talk about in terms of the test, there's a study guide in the packet. It's on page 43. It's actually a few pages before where we are right now. And so if you haven't had a course with me, then this will look unfamiliar, but if you've had a class with me, it's the same style as we've seen before. So the study guide starts here in the middle. There is a list of topics, a list of things I'd like you to be able to do. This is an active list that I'd encourage you to run through and check one at a time. Can I, in number 7, find areas by evaluating integrals? If you can, put a check. If you can't, find some problems where you figure out how to do that. So there's a list of things that I'd like you to be able to do. And then on the next page is some resources. So here are some problems that were never assigned for homework. So if you're looking for more practice problems, you can try those. Certainly going over old homework assignments and quizzes may be helpful. Sample test problems, which are right down here. And then this answers Dave's question, 8.5 by 11 piece of paper, along with page 1, which was the integration formulas reference sheet. Okay, and the sample test problems are there, and if you have time between now and Friday, then certainly you can take a look at the sample test problems. Answer key follows. On Friday, the plan is to just come in and have you guys working on whatever you'd like, and it could be the sample test problems, or it could be going over your old quizzes, or doing homework, or anything. And the last resource on this is that I did make videos of me going through each of these problems, and I'm telling you exactly the character string to search for if you want to find the videos. So 201 sample test 1 problem 5, for example. Although don't search that exact phrase because there's only 4 problems here, so that will come up empty. But that's the form, okay? Any questions on the study guide? Okay. Next resource, I did email this a few weeks ago, but I just wanted to highlight that I made an Excel document where I went through and I took our calendar and I tried to find videos on the Khan Academy website. Any fans of the Khan Academy? Good, a bunch. It's a great site. And so, for example, integration by parts we talked about last class, and there's a link to a video where Colin talks about integration by parts. You see some blanks. I couldn't find stuff for everything, but I did my best. This document I sent in an email a couple weeks ago. It's also on Moodle, so everybody should have access to it. I didn't feel like printing it because it's a bunch of links. So check those out. Some of the things he'll talk about will have a slightly different flavor, and I think it's a good thing to see things from a different perspective. So that's that. Next thing is, okay, so we'll dive back into page 48, part C. Sine to the fourth x cosine cubed x. Maybe before we just jump to the formulas, can we acknowledge that that is crazy complicated? Like, can you think of a function whose derivative is sine to the fourth times cosine cubed? I mean, I have no idea. I mean, it's like, how could a function have that as a derivative? Certainly no function we've seen has exactly that as its derivative. But we do have a bunch of different headings, so find the heading that you think is appropriate for this one. I've got a power of sine times a power of cosine. So anybody have a formula number that seems appropriate? 23 sounds good. Now 23 comes with a paragraph of instructions, so it's not as easy as the other ones. So this one, there's work to do. First, let's identify how much is m and how much is n. M is 4, n is 3. Okay, so we write those down. Okay, if m is odd, is m odd? No, so I'm not even going to bother reading the rest of that sentence. If n is odd, is n odd? Yes, it is. But if it wasn't, then what would m and n both be? What kinds of numbers? They'd both be even, right? If neither of them is odd. And here's the case for m and n are both even, and you have to read some stuff, all right? So all possibilities are there. What if m and n are both odd? Which of the first two sentences do we do? Either one. You'll get slightly different but equivalent answers at the end, all right? But I think we are obligated to do this one right here that you cannot read through. So if n is odd, we're going to let w, this is a u substitution. We'll use u. So apparently we're supposed to let u equal sine of x. Okay, so let's try that. U equals sine of x is the only help we're going to get. All right, so we'll come back here. U substitution, we let u equal sine of x. So the next line is to do what? Du. So what is du? Cosine x dx. So then let's rewrite this original integral. I'll call it I. So my job is to get the u in there minimally. So how do I get my u in there? U to the fourth, right? That's bare bones. And then I've got cosine of x dx. Do you see cosine of x dx in here? Yeah, we got some extra cosine. So how about we start rewriting this guy up here as well? So I'm kind of in between down there and up here. But David's got the right idea. There's an extra cosine squared that I didn't really want. This cosine of x dx, I can find that in the integral. But I peeled off the extra cosine squared. It looks kind of funny to stick it after the dx, but I'm really putting it way out there just to indicate I don't know what to do with this thing. So if it were just this, then what could I put down here instead of the underlined thing? We could put a du. But it's not just that. What else do I have? I got that extra cosine squared. So the question is there anything we can do to rewrite cosine squared? That's good. So we're using one of our favorite identities, a Pythagorean identity that says that sine squared of x plus cosine squared of x is always 1. which means that instead of this cosine squared, we can put something with sines in it. So cosine squared is really subtracting that sine squared from both sides. 1 minus sine squared. Which is really 1 minus what? U squared, right? Sine is U. Which means right down here, instead of cosine squared x, we can put 1 minus U squared. Any questions about any of those pieces?
So if the power is different, they're not.
Yeah, the technique here worked because we let U equal sine, so we want everything down here to get in terms of sine, except we need a single cosine to be absorbed in that du. And so when you take a single cosine out of the 3 cosines, you're left with cosine squared, which we can use Pythagorean identity to get in terms of sine squared. Right. But if this had been, say, a 6th power, and we take one of the cosines out, then we have cosine to the 5th, which we can't wrangle the Pythagorean identity to get us cosine to the 5th. Yeah, if it had been cosine to the 7th, you take a single one out, you'll have cosine to the 6th. Well, here's cosine squared, so if I just cube this guy, then I'll have lots of sines, which is fine. It would be a little bit messy because you'd have to expand. Yeah. Well, yeah, exactly. Do you let U equal sine, and then it's a U to the 4th, or do you let it equal cosine? But with a little practice, you start to recognize why the hint in the formula makes sense. Yeah. We only have a single du. I wrote it in the middle, which is kind of a funny place to write it, but everything in the original integral, which eventually made it over here to this thing, is now down here someplace, term for term. Everybody is down there. We are going to multiply it out. So we're going to distribute the U to the 4th into the blue parentheses. So we get U to the 4th minus U to the 6th. But the du is just a single one that I'm leaving out there at the end. Du doesn't go into both. I mean, it's just sitting there for one, just as one symbol. And then finally, an integral that we can do. Right? Add 1 to the power, divide by the new power. Right, and then we just go back to sine of x. Came from adding 1 to this power and then dividing by the new power. Right, U to the 4th, you add 1 to the power and divide by the new power, and then we do the same thing with this guy. Other questions on this one? So you can see the table is not always just this like gift. You just use it and everything is easy, right? Sometimes you still have work to do. So let's take a look at the next example where there's, again, work to do before we can use the table. Sometimes we first need to do a U substitution to get our integral into a form that's in the table. So let's try it for this one. E to the square root of x sine of 2 square root of x divided by square root of x. Now, I see e's times sines, and then I see this division by square root of x. So let's look at that division part first. Is there a division by square root of x sitting there in any of the formulas? Doesn't look like it, right? I mean, there's some square roots in the bottom, but they have other terms in them. It's not just a square root of x in the bottom. So it feels to me like that square root of x is probably going to become absorbed. It's probably part of the du for some choice of u. Any suggestions on the choice of u? We're going to let it be the square root of x, or x to the half. If we do that, then just rewriting the integral just before we even go too far with this, let's see if it has any potential. What does that integral become? E to the u sine of 2u. And then I've got a fraction, so I'll write a fraction line, but I'll leave it blank. I don't know what to put down there yet. I can't put x. But is e to the u sine of 2u, is that in the table? Products of e's and sines. We had a category. Do we see something that's going to look like e to the u sine of 2u? So Todd says number 8. Maggie also says 8. So this feels pretty good. Like we haven't done the details for the substitution, but without going too far, we can look at this and say, well, if it works, will it be in the table? It is. So let's try it, see if it works. So we'll take our derivative. So if you had me for Calc 1 last semester, do you remember we had a little shortcut for the derivative of a constant over x? Negative the constant over x squared. Okay, so some folks have that memorized. So if you're willing to memorize one other thing, then I'd encourage you to memorize the derivative of a square root of x. It's easy enough to just write it as x to the 1/2 and then do the power rule and then rewrite it. But it always turns out to be the same thing, and I'm comfortable always saying it's 1 over 2 square root of x. So if you feel like adding one more thing to your list of little tricks, that's one that might be worth memorizing. Yeah, so then looking at that, I mean, you can see the yellow highlighted thing. Oh, yes, yeah, but the yellow highlighted thing is right there, right? The square root of x is in the bottom, just where it should be. So let's put our du over here. It's 1 over 2 square root of x dx. So I'm going to circle in blue. What's in this thing that isn't down here yet? I've got the 2 square root of x. That's in here. So what I don't have yet is the dx or the square root of x downstairs. That's what isn't down there yet. So can you solve this thing for dx over square root of x? Yeah, everything is good except that 2. So how do we move the 2? Multiply both sides by 2. So that means that instead of what's circled in blue, we're going to put 2 du. So I'm going to put it down here in blue. 2 du. What am I dividing by? It disappears. It got absorbed. So I'm just going to erase that. That's our integral. For a lot of folks, I know it's tricky when the du has a division in it. So really take your time and go through the details if that's confusing at all. All right, so now we've got that. We can take that 2 and move it to the front, and now all of a sudden we're back in the table. E to the u sine of 2u. So I think we heard a couple people suggest that we use formula number 8. So let's see if we can find formula 8. All right, formula 8, we'll move it up a little bit. E to the ax sine of bx. That sounds good. The integral we were interested in was e to the u sine of 2u. Is that right? And I'll put a 2 in the front. Okay, so we just have to identify the A and the B, and then we can copy the formula and we're done. It's supposed to be e to the ax. How much is A? It's 1. Right? E to the u is what we have. So we're doing actually another little substitution in our heads. Instead of u, what are we thinking? Well, it will become a square root of x at the end, but the formulas on this page don't have u's in them. They'll have x's. So in our minds, we're just translating, we're swapping the u that we have for the x's in the formula. Okay, we have sine of 2u. It's supposed to be sine of bx. How much is b? 2. So you've got your formula. All you have to do is copy it down. Aaron.
Sort of related to what we're doing. I was just going to comment that there were a lot of problems where you had to do use substitution first and do integration by parts. It was getting weird because I had already substituted and was trying to use.
Yeah.
So I started using S. Instead of, I mean, is that, what would you recommend?
I know that there were when we first did U substitutions, there were the ones that I called the weird U substitutions, where you'd have to, you'd plug in, you'd still have X's floating around, but somehow you'd magically be able to convert those into U's by looking at the original definition for U. I think that several of the examples in the integration by parts section are that kind of thing. So personally, I would stay with the U's, but you can show me the example you were talking about. Maybe it was more natural to change letters for you. Yeah. Oh.
Because you end up with like u equals u.
Okay, because of the integration by parts formula has u in it.
Right.
I understand. Yeah, the book uses w for that reason. Yeah. For me, I don't really think about the u's and dv's. I just think about my little arrows, so I'm not so concerned about the letters. Yeah.
Where did the A equal 1?
So the a and b came from this thing. So the integral that we wanted had e to the u and sine of 2u, right? Yeah.
Oh, okay.
Yeah, good. Okay, so let's just talk about our answer here. 1 over how much? 1 over 5, e to the u. And then in the front here, it's supposed to be a sine of bx. That becomes 1 sine of 2u minus 2 cosine of 2u plus c. And we're done, except for just changing everything back into whatever u was. I guess it was the square root of x. So during the group activity, I'll try to get all the answers up here. I wasn't able to write the answers down because I needed to leave the PDF projected for some folks, but I'll try to put them all in there so they're part of this document. Any questions on number 3? Okay, number 4. 3 similar integrals with 3 very different solution methods. Okay, so the first one, 1 over x squared minus 8x plus 15. Second one, same thing, except x squared over. Last one is 1 over x squared minus 8x plus 18. And even though parts A and C look nearly identical, the way we solve them is they really have nothing in common. So let's try each of these. So first thing to do, what kind of polynomials do we have in the bottom for all of them? They're all quadratics. Didn't we have a section in the formula sheet there with quadratics in the denominators? Let's find it. Quadratics in the denominators, part 5. Everybody see it? So we've got all these formulas here when there are quadratics in the denominators. So looking at 26 and 27, apparently it might be useful to do what to those denominators? Factor. So if we can factor, we're going to use one of those two formulas. So let's try. Okay, part A, 1 over x squared minus 8x plus 15. So this is really 1 over, and then go ahead and factor that quadratic. What do we get? X minus 5, x minus 3, and just like that, it's ready to use that formula. So x minus 5, x minus 3. Come back to the back page. I'll put it here, x minus 5, x minus 3. Are we using 26 or 27? 26, 1 over, as opposed to something with x's over, right? So we use 26. How much is a? A is 5, b is 3. Make sure you acknowledge there are negatives built into those formulas. So you got to change the signs of the numbers that we came up with. Okay, so copy the formula down, and this one is done. Any questions on this one? So what do we get? 1 over 2 ln of x minus 5 minus ln of x minus 3. It's done. Okay? Pretty soon after the test, we're going to figure out where this formula came from. So we'll do those kinds of problems without the table soon enough. All right, let's take a look at the next one. What's that, Cole? Yeah, so Cole, I think when Cole factored, he did this, 1 over x minus 3, x minus 5. Is that right, Cole? So Cole factored it in that order. The answer shouldn't change based on the order you factor the thing, right? It's the same answer. It's the same factoring. So what's going on? How much was A for Cole? So his A was 3 and his B was 5, which means that these two terms were swapped, which is unfortunate because there's subtractions. So swapping them changes the answer. But also these two numbers were swapped. So when we had a positive 1/2, Cole had a negative 1/2. And it's exactly the same, right? Like two different negatives come into the problem, but they cancel. Yeah, good observation. All right, taking a look at part B. Well, it doesn't look so bad because we've already factored it. So, so we can write the factored version. So isn't this just the very next formula on the sheet? What did that one have in the top? The cx plus d. Cx plus d. Yeah, let's see. So we have that, cx plus d, which basically means a linear thing upstairs. What do we have in our integral? Is x squared, a quadratic thing upstairs. We can't use it. C and d are constants, and there's no choice of constant C and d that will give you an x squared up there. Bubba? You can. It's a good point. So Bubba says, what if we do this? Integral of x over the two factors times the integral of the other x over the same two factors. Everyone agree that's okay? Well, actually, one of them wouldn't have, right? You only need the factors once because multiplying, we would multiply straight across. Right, so can we deal with this? Well, we could, if we were allowed to separate, then I guess we could deal with each piece. Like you could handle that from number 27, and that one's an easy integral, but can we separate over multiplication? The answer is no, not ever. We cannot separate over multiplication. So when we split things up in order to try to use a formula, we're always splitting up over addition or subtraction. Because yes, you can write it that way, but unfortunately we can't split it at that point. Todd. So yeah, maybe letting a U substitution come in. Yeah, the bottom would end, there would be some effects on the bottom, right? Like it wouldn't, like the top and the bottom are fundamentally different right now. There's an x squared upstairs, but single x is downstairs. And if you change one to try to make it look good, you're gonna, as Garrett points out, you're gonna mess up the bottom one. Maybe it'll work. Dave? Integration by parts.
X squared times 1 over x minus 3 times 5.
So actually that maybe has some potential with what Bubba was suggesting. We could split it up here and then maybe try an integration by parts. That's not a bad idea at all. I haven't thought to do that before, and I'd be curious to see where it goes. But certainly splitting it the way Bubba suggested and then using integration by parts like David suggests, it would go someplace. We'd end up with some new integral, and I'd be really interested to see if we could handle it. So let me, what's that? How would I do it? Let's talk about how I would do it. Here's how I would do it. If the power on the top is equal to or greater than the power on the bottom, we do long division. Yeah. The splitting it and integration by parts is sounding pretty good now, isn't it? Okay, long division. Let's see what we remember. So which one goes, I'm going to write it like this. So which one goes outside? The top or the bottom? The bottom one goes out front. So I'm not going to put it in factored form. I'll leave it like it is here.
Can you reiterate the sentence?
Yes.
Power on top
Is greater than or equal to the power on the bottom. You're welcome. Okay, what goes inside? X squared. Okay, let's see how much we remember about polynomial long division. Yeah, you can stick on some plus zeros if you want to. All right, the basic idea is to take this thing right here and divide it into the thing inside. How many times does x squared go into x squared? Once. One goes up here. So this one is x squared over x squared. And just so we see where the pieces were, it was the outside one going into the inside one. So it turns out you only need to divide the first term when you do the division, and then the 8x and 15 will come into play in the next step in this process. Okay. So we've got that, and now we need to do what? What do you do with the 1? Multiply by the thing that's in the front. So 1 times everything in the front, and we'll copy it down below. X squared minus 8x plus 15. And then what do we do? Subtract. Yeah, be really careful with the signs when you subtract top minus bottom. So because it's so easy to mess up the signs, I like to put that whole thing in parentheses with a big fat negative sign in the front. And we subtract, and what do we get? 8x minus 15. That's right, because there were zeros. Ernie had suggested putting 0x on the top and 0 at the end. And in theory, what we would do is repeat this process now, taking x squared and trying to squeeze it into 8x, but we can't do that. So we're done with the division. You keep going until you can't do any more divisions. So let's just make sure we can write down all the different pieces. We had a 1, and we also had an 8x minus 15, and somehow they have something to do with the original division. So let's see if we can write that here. So I'm going to copy my integral sign. And I'm just trying to rewrite this fraction right here. How many times did the bottom go into the top? It went once. 1 plus, what was the remainder? 8x minus 15 over, what was the original denominator? Same one goes right down here. No, I think we're good now. As soon as the power upstairs is smaller than the one downstairs, we're done. Yeah. Yeah, I rewrote it without it factored, but now it's good. It looks like number, was it 27? Yeah, if you just rewrite that fraction in factored form, we're good. So how about we say we finish with this one? The new thing here was the long division. Now it just looks like a formula and you just copy it from the table. Abby? Oh yeah, I'll just, like I said, I don't want to do the details here, but this is now number 27 where it looks like a cx plus d over 2 factors. All right, so that is that. And then finally part C. So I know we didn't finish part B, but like I said, the only new thing was the division. In part C, what do we try to do first? Try to factor. So go ahead and factor part C. What do we get when we factor?
I got x minus 4 times x minus 4 plus 2.
Mm-hmm. Yeah, it doesn't quite work. So how do we do this one? Tacite, you had a suggestion? Tacite says complete the square. That's a good suggestion. So let's try completing the square. And let me just say, before we do it, ultimately we're going to get down here to something like this. Something squared plus some other number. That's what it's going to turn into when we complete the square. All right? Okay, so will that help us? Well, let's look at the table. Do we have anything here where it's something with x's squared plus some number? We do, 24 and 25. We see it? 24 and 25 both have things that look like what we're about to get. We're not going to get x squared. We'll get something else with x in it, but it'll basically be x squared plus some number. So this is why completing the square is the right thing to do. All right, so let's try completing the square. So I haven't done this in a long time, so you'll have to refresh my memory. So the basic idea is I'm going to copy those two guys, and I'm going to move the plus 18 over here to the side. And then my goal is to add the magic number. Anybody remember the formula for what the magic number is? Half of the middle one. And then what was it? I don't freaking know. What, yeah, plus, what is it? What do we do with this? It's not plus the front one. It's squared. Half of the middle one. Half of the middle one, and then you square it. So how much is half of the middle one? Is minus 4, carrying that negative in. And then you square negative 4, and you get 16. 16 goes right there. That's negative 8 divided by 2. There's the half, and then squared. Yeah. And you can't just go around adding 16 without balancing the checkbook. So right away, I'll subtract 16, but I'll do it over here in the part that I don't care about. When you use this technique with an equation, what you would do is add 16 to both sides. But we don't have an equation, so we have to add 16 and then right away subtract 16. And if we did it right, then the whole point is that this thing in the bracket, you can factor. And in fact, you're going to factor it into two things that are exactly the same. What is this thing in the brackets? Is x minus 4 times another x minus 4. Okay, so we get x minus 4 squared. That's how the thing in the brackets factors. And then 18 minus 16 is just sitting at the end, plus. And so this is actually how David kind of factored it before, but this is exactly what we were after because the two factors he came up with were the same. It's a perfect square. Going back to the integral, what's on the top? It's 1. I'll copy my integral sign. Dx goes over here. Any questions on completing the square? You're welcome. And now it looks like, I forget what number, 22 or 23 or something, 24, kind of. Let's take a look at number 24. So 24 is 1 over x squared plus a squared. Okay, we're almost there, x squared plus a squared. We need this to be x squared plus a squared. Okay, I have x minus 4. What do you think we're going to do? This is a little baby u substitution that we have to do. So here's our baby u substitution. U is equal to x minus 4 without the square. What's du? It's just dx. So that means the integral is equal to 1 over x minus 4 squared becomes u squared. Plus, I'm actually going to write this guy as another number squared. It is the square root of 2 squared. We're writing that because the formula we just saw had x squared plus a squared. That's the a, square root of 2. Instead of dx, du. That's why I said it was a baby u substitution, because all we're doing is changing into a u, but we don't really have to pay for it anywhere.
Is this only the proper way to go about solving this problem? Because we have this table, use it for method.
Yeah, these particular formulas in this section 5, we're going to have techniques which don't rely on the table.
So right now we're just making one table kind of arbitrary.
Right. And then we'll learn techniques that will allow us to do many of the things without the table, but there's still going to be some that will rely on the table. And they're just so complicated that we'll just grab something that's already been done before. Okay, so I think that we're ready to use this formula here. So let's see if we can do it. All right, so what's our integral now? It's a 1 over u squared plus root 2 squared du. Is that right? Okay, and we're using number 24. So for us, how much is a? Is the square root of 2. Because it's 1 over x squared plus a squared. So there's your a. So just copy that formula and we're good. Yeah, right. So what do we get? 1 over root 2 arctan. Arctan. That's not so surprising actually, because do you remember the derivative of arctan? 1 over x squared plus 1. Okay, apparently if it's another number besides 1, you got to pay for it a little bit with this division by a. Fair enough. We'll see that soon. So arctan of x over root 2, except where I said x, should have said u. So 1 over root 2 arctan u over root 2. And then finally go back to the x's. So yeah, the root 2 is a funny thing. So we had u squared plus 4 down here. Sorry, we had u squared plus 2 down here, right? Yes, so that plus 2 needs to be some number squared in order for us to use this formula. So we have to figure out what number squared is going to give us the 2. It would have been easier if this had just been a 9. 9 is how much squared? Is 3. So if it had been a 9 down here, your a would be 3. So you just take the square root of whatever's there. So I got to say, of all the days of material, You know, like, so generally we start with easier problems and then medium and then hard. I feel like this is one of the largest gaps between the easy problems that we started this morning with and then the long division, completing the square stuff that we end. There's a big jump in difficulty between the easy ones and the hard ones. All right, we've got about 10 minutes. There's a group activity with lots of substitution problems there. Any tables that don't have the book, I'll project this thing up here and we can move it around. Maggie? U is the x minus.
It's not x,
Yeah,
x minus 4.
That's right.
But
And then I should have changed this to x minus 4. That's the final answer.
oh, yeah, okay.